Good morning, and thank you to the organizers for being allowed to present here. Today's talk, there is going to be a little modification. I'm going to focus on the Alkyd coating work and not the powder coating work. That'll be a topic for a future presentation. But I would like to introduce to you today who NatureWorks is, a little bit about our corporate background, and get into a case study on the use of Lactide in Alkyd systems. So the quick introduction about NatureWorks is that we've been around since about 1990, started as a Coggio project. We are the single largest producer of polylactic acid, and over the course of the 20 years or so, we've been able to build a polylactic acid business in the thermoplastic semi-crystalline application areas, starting initially as a project, and then through a variety of joint owners, Cargill Dow, Cargill Teijin, now Cargill PTTGC. We are in a position where our polylactic acid business is now approaching 2 billion pounds of aggregate sales since 2005. And so with that, we're able to have in our company the opportunity to look at new ways of using Lactide, taking some looks and some risks and some other opportunities for Lactide in applications such as coatings and adhesives. And I want to share with you today what we have going on. So a little introduction about the chemistry. I'm a chemist by training. I talk with molecules. NatureWorks has a Lactide platform to make PLA. And simply speaking, in a nutshell, it is a fermented product from agrochemical sugars to L-lactic acid. Lactic acid is dehydrated to form lactide. That's our intermediate from which we can undergo, the molecule can undergo ring opening polymerization and form a variety of different high molecular weight semi-crystalline thermoplastic products. These products are well established already in the industry, most notably fibers, nonwovens, films, sheets. Some of the more common application, paper coatings where they exhibit excellent oil, grease barrier resistance, heat seal properties, ink receptivity properties. But on the way for lactic acid to lactide to PLA, there is a little bit of a side reaction that goes on, and that is in the dehydration process of lactic acid to lactide. There's actually several different lactide molecules are formed. So I won't get into the organic chemistry of all of the optical properties about lactide, but it is an optically pure L isomer. In the conversion to lactide, it can racemerize, form the D isomer, and then during the dehydration, you can actually get combinations of D lactide, L lactide, and mesolactide, where of these two optical centers, one is the L orientation, one's the D orientation. The L and the meso are key building blocks for us, and I'll be spending most of my time today talking about these two molecules in an Alkyd. So having said that, we now as a company take lactide to PLA. We're taking that lactide technology and moving it into lactide for performance chemicals. So again, same sort of thing, but now our building block is going to be something we can create other derivatives out of. We don't need to go to 75,000 or 125,000 molecular weight. We don't need to rely on semi-crystallinity to drive our properties. We have other formulation handles and chemistries that we can utilize that make these intermediates useful in coatings and adhesives. This next slide here is a transition slide to share with you the chemistry about the lactide, talking about it as a polyol, although later in the talk I'll transition to the Alkyd chemistry. But just to give you an idea what happens for the chemists in the room, the cyclic lactide system is reactive towards a variety of nucleophiles such as alcohols, dialcohols, triols, and so on. The reaction based on whether it's a meso or L, but fundamentally is a 100% solids reaction. It's fast, there's no water loss, and you can ring open the molecule and you can actually get dinucleophilic addition on both sides of the molecule. You end up with a diol if you start with a diol, triol if you start with a triol, and so on. If we look just at the polyol systems, and this will actually be a subject of a future talk later this fall, we have some formulation handles here. What's our R group? What's our degree of polymerization? what's our ratio of meso to L. These sort of formulation handles at these lower molecular weight resins actually enable a greater influence on the physical property. If the molecule has a molecular weight of 100 or 125,000, the influence of the end group or the influence of the initiator is relatively minor. But if the molecule has a molecular weight of 10,000, 20,000, 3,000, of course we can end up with a greater influence due to initiator and end group species. And therefore, broadening the TG range, making it amorphous or crystalline, manipulating viscosity. As this reaction is shown, you do end up with secondary hydroxyl groups, not primary. But again, it becomes a useful intermediate that we're looking to use and have used, and our customers have used in a variety of applications outside of traditional thermoplastics. So with that, I'll talk a little bit about now transitioning into the alkyds and the topic of today's talk. So alkyds, alkyd resins, as we know, and as many people in this room know, basically they're a polyester resin. They're based on a combination of phthalic anhydride, pentaerythritol for the most part, and some fatty acid with some unsaturation, so-called natural oils or natural drying oils. Often the chemistry involves the use of a chain stopper to prevent gelation because of the highly branched nature of the phthalic anhydride pentaerythritol. There's a need to be careful about the alkyds gelling as you approach high conversions and high molecular weights, and therefore a chain stopper such as benzoic acid is used. Now, looking at the lactide molecule, what can happen is that lactide is actually able to replace some of the equivalents of the pentaerythritol and some of the equivalents of the phthalic anhydride. And therefore, it's possible to remove not only some of these equivalents, you don't need to use benzoic acid anymore, at least in the reaction conditions we use, but also now the lactide fundamentally changes the molecular architecture of your alkyd. Okay? Whereas mostly in the chemistry where pentaerythritol and phthalic anhydride are together, you always have phthalic anhydride being ring opened with and by pentaerythritol. With lactide in the mixture, that's not the case. Lactide, once it's ring open, has an alcohol group. That alcohol group reacts with the anhydride, and you can now start to open up the alkyd structure, making it highly branched, but also a little less, it's still branched, still has the oil, but it's also a little more flexible and has a little more of degrees of freedom because of the linearity of the lactide. I show here a couple repeat units where it's one lactide unit. Lactide can homopolymerize. You can have multiple repeat units. And so with that, I wanted to just have you, for the chemists and molecular architects in the room, think about that as we go forward and talk about the case studies involving the alkyds. So we did a case study involving a variety of formulations looking at a medium oil length alkyd. These were around tall oil fatty acid content of 47 to 48%. We looked at changing and incorporating lactide up to 25% by weight. I'll talk by weight in these tables, but obviously moles matter, and so the stoichiometry was maintained such that we could obtain similar degrees of polymerization, similar acid numbers, and get at roughly as best we could an apples and apples comparison as we replaced some of the molecules with the lactide. The incorporation of 25% lactide was our limit for this study. Again, I talk about replacing the phthalic anhydride and the pentaerythritol. No need for benzoic acid. Did solvent-borne coatings, standard dryer systems, and the results of which we'll share with you right now. So after making the resin, I want to start kind of walking you through what was the influence of the lactide on the resin, what was the influence of the lactide on the coatings. So one of the biggest things that's known already about lactide, it's been reported before, is a very, very significant and positive influence on the resin viscosity. This graph here shows a series of curves where, relative to the control in the red line, we look at 7 to 25% incorporation of L-lactide, similar amounts of amezolactide, and we look at the acid number on the x-axis versus the resin viscosity on the y-axis. The details of the viscosity, cap viscosity measurements at the temperature there, 120 C or something. The point I want to show up is that as the reaction progresses, getting at similar acid numbers, therefore similar degrees of polymerization, all of the lactide systems show a consistent decrease in the resin viscosity at any of the acid numbers. In this particular study, we stopped our reactions between an acid number of 8 and 10 milligrams of KOH per gram of resin. When you look at these curves here, you see the L and meso compared. There's not a big difference in the effect of the resin viscosity. Whether you use an L or a meso, they behave relatively the same. But you do have 7.5%, 15%, 25% incorporation of lactide showing a drop in viscosity. So what does that mean when you have the final resin you want and you want to make a solvent-borne system out of it, is that it's possible to go to much higher percent solids and therefore formulate a lower VOC resin with the lactide. Again, marching here left to right, I show a percent solids on the x-axis versus solution viscosity in a 4:1 mineral spirit xylene. We look at, again, left to right, no lactide, 7.5% lactide, 15% lactide, 25% lactide. Here again, possible to say, for example, at a 5,000 centipoise viscosity, you can see that you can go from about 55% solids to about 65% solids. And we just did a little bit of work in a different solvent system. And we actually found that butyl acetate instead of the mineral spirit xylene, it was possible to get near 80% solids and keep the resin and keep the solution viscosity to under 5,000 centipoise. So that's a very significant drop in solvent content, lowering VOCs, opening up the opportunity to use this, say, in blending and formulation. So these were positive benefits of lactide in the Alkyd resin system. Here now in this graph, I want to show you a little bit where the L and the meso do show a little bit difference in effect on the resin. This is resin glass transition temperature, so the polymerization's done, resin's dried out. We measure glass transition temperature as a function of lactide content. Again, keep in mind, I said earlier, the lactide opens up the structure. You actually see that here in TG, because there is a drop in TG from the control. No lactide at about 4 C. Going here again, mesolactide, dropping it down to about minus 14 C, so about an 18-degree drop with the mesolactide. When you're over here with the L-lactide system, there is still a drop when L-lactide's incorporated into the resin, but the TG does not drop as much, only about a 10-degree difference at a 25% incorporation. And then, being a chemist and you mix things, we looked at mixtures of a meso and an L, and in fact it was kind of interesting. It looked like the L meso dominated the glass transition behavior of the resin, and even though this is at a 25% incorporation of total lactide, it's very similar to 100% L as opposed to 100% meso. And that was reproducible with the, because initially it's like that didn't seem to make sense. So that was a surprising finding on the resin. So again, the conclusion there I just talked about is that the meso has a greater impact on glass transition temperature of the resin than L. So this here is some performance data. What I'm trying to show you here, I want to walk you through this over the next couple of minutes, is focus on, we're going again left to right, control, and then a series of Alkyds where we're either at a 15% total incorporation of lactide or 25% total incorporation of lactide. These are different mixtures, if you will. We can explain those later. We're looking at implications here of some properties. So solvent-borne Alkyd, coated on metal, fully cured. We let it go out to a 30-day cure using the standard oxidative dryer. 50 micron dry film thickness, characterize the films. We had here, see, the viscosity, I already talked about the impact of that. Both the resin and the solution viscosity, a significant drop there. You can see here that we kept the molecular weights by GPC values very similar. So again, trying to maintain that this viscosity impact is not a molecular weight effect. The viscosities, the GPC value showing up here between about 3,500 and 4,000. I think there's one there that might be closer to 5, but in the same ballpark, if you will. The other thing I want to point out, Persaud's hardness. This is, again, looking at the rate of cure. We looked at hardness build at a 10-day and 30-day cure, the control versus the 15% versus the 25% incorporation. Hardness build with 15% lactide relative to the control by Persaud's was very similar. The 10-day and 30-day hardness indicating a similar rate of cure and a similar hardness build or cross-link density. You can see here at the 25% lactide loading that there is a slight reduction in the hardness of the lactide of the Alkyd made with lactide at full cure. Some of the things we also looked at here were crosshatch adhesion. Now, these were done using a method based on the European scale. So 0 adhesion is actually good. So it's the exact opposite of the ASTM scale. But the crosshatch adhesion is done the same way. So the control showing effectively very poor adhesion by crosshatch, really ripping the coating off from the metal. 15% lactide showing a significant improvement, getting a 2 rating on crosshatch. 25% lactide showing a 0 rating, or in other words, the best adhesion you can get by crosshatch. The real big impact, no pun intended, was actually the front and reverse impact testing using the ASTM or ISO method for drop impact test. So using a 1 kg weight up to 1 meter length and drop, so in other words, about a 10 Newton meter force falling on the samples. You can see here that the reverse impact of the control actually started to fracture and crack at less than 5 centimeters of a drop impact force onto the coating, or even the lactide here showing, in some cases, being able to absorb the full impact force of that 10 Newton meter drop impact test. So a very, very significant improvement in drop impact testing of these Alkyd coatings. I think that goes back to, if you think about, again, that open structure, the Alkyd is a little tougher as a result of lactide in its molecular architecture, as opposed to having something that's highly branched. The mandrel bend showed similar results, but since it's not a rapid impact test, the results appeared to be somewhat similar, lactide showing a modest improvement using a mandrel bend. The other thing we notice on a Tabor abrasion test using the C22 wheel, so a common wheel used for testing coatings. I'll walk you across the results here. So there's a lot of data in these curves, or in these bar graphs. See here, okay? So again, we have here within the bar set, we talk about a control. We talk about 2 systems at 25% lactide and 1 system with 15% lactide. And then we look at 250, 500, 750, and 1,000 cycles. So again, going from left to right, you show an increase in weight loss as a function of how many abrasion cycles. Many know higher weight loss means is an indication of poorer abrasion resistance. And what we found going across this is that the lactide-based systems, particularly here at the 15% loading, really showed a significant reduction and weight loss, and therefore an indication of improved abrasion resistance as a result of lactide. And that's at a 15% lactide incorporation. Again, these bar graphs are the results of multiple tests. We wanted to go back, particularly in this case, to review them, and so it's actually 2 different resin sets made of repeats that we went back and tested, and we see the results here. So these are average values from repeated tests. On coatings, solvent resistance is a big issue. We're thinking in this area more along the lines of a wood coating application. So we're looking at spot testing as a result of a solvent attack, or delamination as a result of a solvent attack. On the coating, we looked at water oil and wine. That was a good combination. That was a good day. We looked at ethanol, and we looked at acetone. So here, just showing you quickly results of what happened to a spot test. Did it leave a shadowing spot, or what happened to blistering? Did we see evidence of coating damage and delamination? A 3 and 24-hour test. Basically, a lot of zeros for water, wine, and oil, vegetable oil. A lot of 5s, meaning really, really poor results for acetone and MEK. It's the reason those solvents are used as as paint removers for all of the systems. But we did clearly see a measurable benefit of the lactide incorporation in the ethanol. So kind of this transition solvent area, we're seeing some indications here that the solvent resistance with the lactide in the polymer resin is showing up some improvements. We did then also some exposure testing. So here again, fully cured panels on the metal. I want to point out that it was actually a 30-day cure, not a 14-day. Apologize for that typo. Again, fully cured systems, as like we did in the other series. We did standard UV exposure testing, basically following those ISO standards. Basically, it's exposure to some humidity, it's exposure to a dry temperature, and we looked at change of optical properties over the course of 7 to 28 days. So this represents a 28-day testing. The data summary here, I'll show a few of the values. First, looking at UV stability in terms of a delta B value, so a change in yellowing index. This is the yellow-blue scale. The initial B values here of the coatings. And the other thing I need to point out, these are pigmented, so we used a 20 PVC, 20% pigment volume concentration of these coatings using a standard TiO2. Didn't really work to optimize this, but just so you know, it's a pigmented system. The other ones that I reported earlier were lacquers. There was no pigment there. So I wanted to clarify that. Initial B values, control was a 2.2 that we measured, 2.3, so really not a difference at 15%. Maybe an indication of increased yellowing, 2.8% at the 25% loading. And here we now look at our delta B values. So what's the change from those initials as a function of time? What we are seeing is that the delta of the lactide systems after the 28 days are significantly lower than the delta of the control system, less yellowing. And this is really something that could be anticipated to some extent because of the fact we're removing aromatic from the matrix and putting in aliphatic. Delta E follows the same thing. So instead of just the blue-yellow, this is the total color spectrum, but the same sort of performance indicators we're seeing. Here on the UV exposure, we did gloss valuations. Out here, rather than showing a delta gloss, I'm showing initial and then the actual values. But all of the coatings came in at about the same gloss level with the way we made them. They were about 80 gloss value units at a 60-degree gloss. There is a decrease as expected across the gloss spectrum or the gloss values with time. We are seeing here that the controls seem to have held in better than the two lactide systems. Not a big difference, but also not insignificant either. We really didn't, again, work to optimize this. Was there something in how we mixed it? Not optimizing something with the pigment or so on. But an indication anyways that there's good retention of gloss and a good initial gloss. So these spider charts kind of summarize everything I've told you. They're in our brochure. They're at our booth. I won't walk them through you here. We can talk more in detail at our table. Basically summarizes what we were talking about earlier. Generally here in summary, so lactide and alkyds, it can go into these polyesters. It can go into alkyd systems. Can replace both penta and phthalic anhydride. Customizable building block with the different types of lactides. There's some synergies that maybe could be extracted there. We see very, very good viscosity behavior, very good drop impact behavior and abrasion resistance. We're seeing some good results here with some of the solvent resistance and adhesion and so on. So we believe it's another tool, it's another capability to add to an alkyd or a polyester resin system. We believe there's going to be benefits across many of the resin systems other than just alkyds. We're continuing to study this. With that, I want to acknowledge our NatureWorks and team. They put a lot of effort into this, and there's a lot of people that help make this presentation possible. So with that, I would be glad to take any questions. We are at table 45, and I want to make sure you guys get to lunch. So thank you with that.